state and apply Coulomb's law. You will define electric field strength and apply the derived equations. You will also draw electric field lines around charged objects, calculate work done in moving a charge in an electric field, define and explain potential difference, and you will also define and explain the concept of potential energy. Following are the key concepts that we will focus on. We will look at Coulomb's law, electric field strength, electric potential, potential difference, electric potential energy, and the concept of work. There are basic concepts in electrostatics that we need to look at. By definition, static electricity is the build-up of electrical charges on the surface of a material. The word static means there is no continuous current flow. Static electricity is usually caused by friction. For example, if you've got a cloth and you bring a comb to it and you rub the comb on the cloth, and then you have pieces of paper as shown here. If you bring the rubbed comb onto the pieces of paper get attracted by the comb. Now, to explain that, we need to understand that if an object loses electrons, it becomes positively charged. If it gains electrons, it becomes negatively charged. In other words, during the friction, if it gains or loses electrons. If it has a positive charge, it then attracts the electrons, the negative charges on the paper in this case. And if it has a negative charge, it then attracts the protons on the paper. A closer look at the concept of attraction and repulsion. Repulsion takes place between like charges. Like these two positively charged objects tend to repel one another. Attraction takes place between unlike charges. A positive charge and a negative charge tend to attract one another. It also takes place between a charged and a neutral object. Over here, we have a negatively charged object. Here, a neutral object. The same number of positives and negatives. When the negatively charged object approaches, the electrons get repelled, making this side of the object partially positive and that side negative. And therefore, this negative charge attracts the positive side, and so we get attraction here as well. Now, we investigate the concept of electric fields. An electric field is a region in which an electric charge will experience a force. It is represented by a pattern of what we call field lines. Now, an electric field line is a tangent line drawn to the direction of the force that a small positive point charge experiences on that electric field. For example, here we have a negative charge and a positive charge, and there's an electric field between them. If you put a positive point charge over here, it experiences repulsion and attraction by this side. So your field lines will look like this. And that's the direction of the force that it experiences. Electric field lines take various patterns depending on the charges involved. The electric fields can be uniform or non-uniform. We get uniform electric fields between parallel plates and non-uniform electric fields as shown by field lines around point charges. For example, around a positive charge, that is the pattern of the field lines. Notice they move away from the positive charge. Around a negative charge, the field lines look like that, towards the point charge. Between like charges, which are looking like that, that is the pattern of the field lines that you'd observe. Notice on both point charges, it's moving away. Between oppositely charged parallel plates, as shown over here, that is the direction of the field lines. You have a uniform electric field moving from the positive to the negative. Following are the properties of field lines. Now there's a diagram just to remind us of what we are talking about. Number one, they move from the positive charge to the negative charge. The direction is always from the positive towards the negative. Field lines never cross, so you must never cross them when drawing them. They surround the charged object in 3 dimensions, even though we don't show that in our diagrams. They are perpendicular to the charged object. Field lines are closer together when the field is strong and further apart when the field is weak. For example, closer to the point charge over here, we have a stronger electric field because the field lines look much closer together. As you move away from the charge, then they move further apart from each other, so the field strength weakens over here. Also, the number of field lines is proportional to the magnitude of the charge. In other words, when we have a stronger charge, we should actually draw more field lines to indicate a stronger electric field. There is a law called the law of conservation of charge. According to this law, charges cannot be created nor destroyed, but they are merely transferred from one object to another. In other words, the amount of charge in a closed system remains constant. Now let us consider 2 charged spheres as shown over here, a plus 6 coulomb and a minus 14 coulomb, that are then brought in contact with one another. Now when they come together, electrons move from the more negative, which is the minus 14, to the less negative sphere, like that. Now, when they are in contact, the charge is spread evenly over both spheres. So, the total charge for both spheres becomes minus 8 coulomb. Upon separation, each sphere carries half the total charge of the 2 spheres. So when you separate them, each sphere will be minus 4 coulomb and minus 4 coulomb. A challenge for you: 2 metal spheres of equal size on insulated stands have a charge of plus 8 microcoulomb and minus 6 microcoulomb respectively, as shown over here. They are then brought into contact. Now, calculate the new charges on each sphere when, after the contact, they are then separated. What is the charge on each sphere? Now let's get started. First of all, we must calculate the total charge of the system. To do that, we simply add the 2 charges, the plus 8 and the minus 6 microcoulomb, and the total charge when the 2 are together is plus 2 microcoulomb. And then we separate them and calculate the charge on each sphere. To do that, we simply divide the total charge by 2. So upon separation, the charge on each sphere is plus 1 microcoulomb. The force between charged objects is explained by Coulomb's law. Coulomb's law states that the force of attraction or repulsion between 2 electric charges at rest is directly proportional to the product of the charges, and it is inversely proportional to the square of the distance between the charges. So the formula for Coulomb's law: F equals to K Q1 Q2 over R squared, where Q is the magnitude of the charge and the unit for charge is coulomb with the symbol C, and R is the distance between the charges measured in meters, and then K is what we call Coulomb's constant, and the value for K is 9 times 10 to the 9 Newton times square meter per square coulomb. An application of Coulomb's law: when a positive charge of 6 microcoulomb and another of 10 microcoulomb are placed a certain distance apart, the force of repulsion between them is 54 newtons. Calculate the distance between the charges. Before we start, we need to look at what we are given. The force is 54 newtons. Charge of Q1 is 6 times 10 to the minus 6 coulomb, and Q2 is 10 times 10 to the minus 6 Coulomb. The formula for Coulomb's law that we use, F equals to K Q1 Q2 over R squared. And then we make our unknown R the subset of the formula. So R squared is equal to K Q1 Q2 divided by F. And so we substitute for K, our constant, for Q1, for Q2, and for F. And so the units cancel, newtons cancel with newtons, and Coulomb cancel with each other. And so the value for R is equal to 0.1 meters. Next, we investigate the concept of electric field strength. By definition, electric field strength at any point, it is the force that a positive unit charge will experience at that point. So the formula for electric field strength is basically force divided by charge. In symbols, E for electric field strength is equal to F divided by Q. Therefore, a force acting on a known charge in a known electric field is given by the formula F equals to Q times E. F being force in newtons, Q being charge in Coulomb, and E being electric field strength, and the unit is Newton per Coulomb. Now, what if the electric field is around a charged sphere? How then do we determine the electric field strength? Well, here we have a charged sphere, Q, and if we have a small test charge, small letter q, that we place a distance r from charge q, capital letter Q, according to Coulomb's law, F equals to K small q big Q divided by R squared. But also according to our recent definition of field strength, F is equal to Q times E, which is our second equation. If we combine equation 1 and 2, we come up with the following that you see over here. And small q cancels off with small q. And therefore, the formula that we use to calculate the electric field strength around a charged sphere is E equals to KQ divided by R squared. K is still Coulomb's constant, Q is the magnitude of the charge, and R is the distance between them. Another challenge for you. Calculate the electric field strength at a distance of 10 to the minus 2 millimeters from a charge of 1.6 times 10 to the minus 19 Coulomb. Again, we are given Q of 1.6 times 10 to the minus 19 and R is 10 to the minus 2 millimeters. We are to calculate E, the electric field strength. Before we continue, we need to convert the distance from millimeters to meters, and to do that we divide by 1,000. So we divide 10 to the minus 2 by 1,000. So our distance R is 1.0 times 10 to the minus 5 meters. Now we calculate E equals to KQ over R squared, and we substitute for K, for Q, and for R, don't forget to square. And therefore the electric field strength in this case is 1.44 times 10 to the minus 4 Newton per Coulomb. Next, we look at electrical potential energy, whose symbol is U. Electrical potential energy is the capacity of a test charge to do work due to its position. Let's consider a fixed positive charge, charge Q. A nearby positive charge, small letter q, experiences a repulsive force and therefore has potential energy. Now the potential energy U of the test charge, small letter q, at a distance r from the positive charge of the source charge, capital Q, is determined by the formula U, in other words, its potential energy, U is equal to K, big Q, small q divided by R, where K is still Coulomb's constant. Also, we sometimes talk about the concept of electric potential. Now, consider a non-uniform field around a positive sphere. There you have our positive sphere, and the field is non-uniform. And then consider a positive test charge placed at a point B at a certain distance R from the charge Q. There we have our positive small q placed a distance R from big Q, and let's call that point B. Q has electrical potential energy U at that point B due to the distance from Q. It's got electrical potential energy due to its position at point B. By definition, electrical potential at a point is the potential energy per unit charge at that point. So, electrical potential V at that point B is equal to electrical potential energy U divided by the charge, in this case small q, where V is measured in volts, electrical potential in volts, and the symbol is capital V, and the unit is also V, and then U is the potential energy, and the unit is joule, and the symbol for the unit is J, and then of course Q is Coulomb, the unit for Q is Coulomb, capital C. Then we talk about electrical potential difference. Now if you consider the same test charge, small q, there it is at the distance B, and then it gets repelled to a point A, as shown over here. It gets repelled to that point A. The electric field does work on Q. So the electric field around big Q does work on small q to repel it from point B to point A. As Q moves, its potential energy decreases as its kinetic energy increases as Q moves from B to A. This implies that the potential energy of B is greater than the potential energy of A. So to move the charge from A to B requires an external force. In other words, work must be done by an outside force to move the charge from point A to point B. And that work done is equal to the change in energy. The energy at B, potential energy at B minus the potential energy at A. So, the electrical potential difference is the amount of work done per unit charge to move a positive charge from a low potential point to a high potential point. The amount of work done per unit charge Q to move a positive charge from a low potential point at A to a high potential point at B. And our formula to calculate the electric potential difference would be the potential at B minus the potential at A, or purely the amount of work done to move the charge from one point to the next divided by the magnitude of that charge. And to simplify that formula, V equals to W over Q. V in volts again, W in joules, and Q in Coulomb. Now to close off this lesson, let's look at the summary of the definitions that we've spoken about. Remember, studying electricity, it is the build-up of electrical charges on the surface of a material. Electric field, a region in which an electric charge will experience a force. The law of conservation of energy says that charges cannot be created nor destroyed, but they are merely transferred from one object to another. Coulomb's law, the force of attraction or repulsion between two electric charges at rest is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Electric field strength, remember, the electric field strength at any point is the force that a positive unit charge will experience at that particular point. Electric potential energy, the capacity of a test charge to do work due to its position. Then we talked about electric potential at a point, which is the potential energy per unit charge at that point. We also spoke about potential difference or electric potential difference, which is the amount of work done per unit charge to move a positive charge from a low potential point to a high potential point. If we look at the summary of the equations that we have dealt with in this lesson, the equation for Coulomb's law, there it is. And these are the equations that we talked about when we talked about electric field strength. Remembering this one is the equation that we use for electric field strength around a charged sphere. The equation for electrical potential energy is this one. Equation for electrical potential, and the equations for electrical potential difference. Now we've come to the end of this lesson, but additional challenges for you can be found in the book Study and Master, the grade 11 copy. On page 115, activity 1, you will find additional challenges dealing with Coulomb's law and electric field strength.